we basically show how the formula that we have derived the first leg of this lecture are work in practice. So first of all, we examine this J rho, which is this reduced moment of inertia. So let's look let's see how it looks like. So if we carry out, if we have now we focus on some exemplary cross sections, and so we focus on a rectangular cross section. We carry out the integration of this x r squared times this j divided by j, and we carry out the integral, and we get a logarithm formula with a I, which is so if you look at the final formula, there is 12I over h over rho squared divided multiplied by a factor. In the if you look this where I is the standard moment of inertia. So what happens for we can get a similar expression for the circular cross section, and this by using polar coordinates we can carry out also this integration of relative to j rho, and we obtain this other formula. And these two formulas, but maybe for you are a bit obscure, can be illustrated graphically. These are illustrated graphically in these plots. So we have to the left in this figure we have j rho over I for a rectangular cross section. And to the right, we have no, for both the rectangular and the circular cross section, and while for the to the right we have the shear reduced shear correction factor plotted for the rectangular cross section and the circular cross section. And what we see is that looking at the moment of inertia, we see that the moment inertia reduces to the value of the straight beam when r over rho, when basically this r over rho is or h over rho. R over rho is relative to the circular cross section. So it's the radius of don't be confused. R is the radius of the cross section. Rho is the radius of curvature of the beam. So we are assuming a circular cross section. The axis can be can have any shape. So it has a curvature radius rho, while R is the radius of the cross section. If we take this ratio varying from 0, which means that rho goes to infinity, the curvature radius of the beam goes to infinity, to 0.5, which means that it's basically is a very high curvature beam. Then we have this curve. This curve, we can see that the variation of the moment inertia can go up to 10%. The deviation of this ratio can go up to 1.10. While for the rectangular cross section, we can have either larger variation in the moment of inertia of the reduced moment of inertia with respect to the classical moment of inertia, which can go up to almost 1.20. Regarding the shear correction factor, also this shear correction factor can go up to 1.50, starting from a value of 1.20, if we refer to the rectangular cross section. And so this is due to the curvature of the center line. So we see that obviously it's not customary to have a radius to have the ratio r over rho or h over rho equal to for example 1. H over rho equal to 1 means that basically h over 1/2 of h. It means that basically we have the introduce of the beam is close to the center of curvature. So it's a very, very strongly curved beam, which can also be analyzed in some cases. I told you that we can apply this to hooks, to studying hooks. We can apply this theory for hooks that are used in mechanical engineering, and so we can go up to h over rho equal to 1. But if we are in the region with h over rho equal to 0.1, for example, which is more common, then you see that this I rho, j rho is close to I, and also key rho is equal to the 120, almost equal to 120, the value for the straight beam. Now, what happens for the stress components? So, if for the sigma TT, if we first examine the case of a rectangular cross section, we obtain that the sigma TT, and we use the J rho that has been updated here, so it's cumbersome. So if you use the J rho, we obtain it here. In the expression, the generalized expression of the generalized Navier equation, Navier formula. So this is still with J rho, not expanded. This is the formula for sigma TT. But and we have these two values, the maximum and the minimum, that are not coincident and each other. And we can also obtain the sigma TT, which is so we have so this is the sigma TT this is for the rectangular cross section. This is for the circular cross section. Pay attention that we have not replaced the expression of J rho here. Otherwise, we get a very nasty formula. We get very nasty formulas because the J rho of the circular cross section is this term, while the J rho of the rectangular cross section is this quantity. So we have not replaced these quantities in this question, but this has been done numerically in these plots, so that we will look now. So this is the sigma TT. First, let's look at the first two plots, the sigma TT. The sigma TT is linear in the obviously in the classical beam theory, the straight beam theory, the Navier formula. Indeed, we find this linear profile of sigma TT, which has been normalized times m over b h squared, in the case in which h over rho is 0. But if h over rho goes to 1, you have to understand 1 is the case. So if we have I can make most probably I have to remove sharing. See, I will do myself. Whatever happens, happens. So I think that now you can look at me and you can look at the blackboard. Okay. So h over rho equal to 1 means if we have this is h, this is the our grade. This is h over 2, h over 2, and then we have rho. So if the center, if we have h is equal to rho, it means that here we'll have another h over 2, and then we get the center of curvature, the local center of curvature of our beam. So this is what we are representing now. For this is the case with h over rho equal to 1. Means we have the center of curvature is at h over 2 from the introduct of the beam. So this means that h is equal to rho. And so this is a very magically curved beam. We cannot go if h over rho is equal to 2. We will have that if a is equal to 2 would be that the central curvature is at the intervals. So which we get there. So it will be a degenerate. So we don't want, we will never go to this part. So this is the case of a very strongly curved beam, which can be some book usually for hanging loads. You know, this we can have kinds of you can have a geometry that is very curved and maybe it's not very reinforced here. So, or the other way around, upward, whatever. So this is the case that we are, and also this is for h over rho, and for in the case of h over in the r over rho. So this is the case of a section with the section with h and v. If we have a circular cross section, now I have to use all my nodes. Okay, we find my K. For r over rho, we have r over rho also equal to 1. So in the case of a beam with a circular cross section, is the same. So this will be it's the same, exactly the same thing. So we can have r and we can have the limit case we are realizing which the center curvature is a distance r from the input. And so, okay. So if we go back to sharing the screen. So this is what we get. So in this limit case, h over rho equal to 1, or this is r rho equal to 1. This is there is no, but it's the same thing. With the same, the three curves are parameterized for the same values of r over rho. So in this plot, we see that we have a distribution that deviates from the linear one, and we have a larger stress at the introdos than at the extradose. So this corresponds to the fact that we have the arc length is smaller at the introdos than at the extradose. So,
also the neutral axis.
yeah, also the neutral axis moves downward if you look. So yeah, the neutral axis moves down. And so what is the maximum value? So if we have the straight beams, we have 6 because basically we are sigma tt divided over mb h squared. If you remember, for the straight beam, this would be 6. While we can go up to 8 in the hook case. So the maximum stress will be 6 over 8, which is 8 over 6, 4 over 3. So it's markedly larger value. Now also here we start from 8 because this would be for the circular beam, this the maximum stress for the straight beam will be m over p r cube multiplied by 4. Since we have 2 at the denominator, there should be 8 here, but we go up to 12. And this is for the normal stress. What about the normal the normal tangential stress, so the classical normal stress? Then we have the radial stress. Let's call this normal stress, and this other one radial stress. They are both radial. They are both normal stress, but this is the normal stress on the cross-section plane. This is the normal stress on the radial plane, on a plane that it has. That is whose normal is the radial direction. So no, this is not. Sorry, this is not yet sigma RR. I don't remember if we have sigma RR. This is another way of plotting this. We are still referring to the normal stress. Okay, Gianni Germano is arriving a bit late. It doesn't matter. And now these other two plots, we are plotting only the maximum value for these two stress distribution divided by this scaling factor, and we are letting h rho continuously to vary. Instead of having 3 values, we have h over rho continuously vary, or r over rho continuously varying from 0 to 1. And we see how this, starting from 6, how this varies, and for the sigma tt, and this they have two ways of plotting this. And this is in absolute value. This is divided sigma tt for the case of the straight beam. So what we see basically from this plot is that the deviation is larger, its percentage is larger for the circular beam than the rectangular beam. But still the difference can be 60%, 60%, which is a large deviation. Obviously, this large deviation is observed in very strongly curved beams. And we have also, and then we will close this discussion, we can also compute the reduced static moment that appears in the generalized formula for the shear stress. We can compute reduced static moment, accounting for curvature. We are examining the case of a rectangular cross-section. Then we get this expression of the Jurasky formula modified for rectangular cross-section, accounting for curvature. And we can also derive this similar formula. You see there is a logarithm here appearing in this formula. So how does formula look like in a plot? Here, these are the plots. So again, first we look at the distribution of the TRT over the cross section for three values of these factors h over rho and r over rho. And we see that we have the parabolic profile that is typical of the straight beam that deviates into a kind of more complex, more complicated profile with a logarithmic term when h over rho goes to 1. And we see also that the maximum value of the shear stress also significantly increases. And this also both for the rectangular cross-section and from the circular cross-section. And if we plot the maximum value as in absolute values, or in referred to the value of the classical Jurasky theory, we find that this is, for example, for the tau RT of the rectangular cross-section, we know that it's 1.5, the maximum tau divided T over BH, which would be the stress predicted by the theory with no correction for the reactive part of stress. And this is the profile for the circular cross section. So we have a less marked increase of in percentage as compared to the normal stress that can increase up to 60%, as we have seen, 50, 60% for in terms of the maximum value for accounting for strong curvature. In case of tangential stresses, we have a less marked increase, which can go up to 20% or something bit lower than that, accounting for curvature. We don't have plots for the sigma radial, I'm sorry, but they can be obtained from the formulas that we have seen before. But these are the main stresses that are the most important stresses that one needs to compute in a beam, the normal and the shear stresses. And so this is what we get when we have a curved beam. I want just to conclude that these corrections due to the curvature, which are derived from the constitutive equations, are relevant in very particular cases, which most often do not happen in civil engineering. In civil engineering, our arches have a moderately large curvature. We never get to h over rho equal to 1 in civil engineering. So civil engineering applications, this effect are less relevant, and we can apply the constitutive equations of the Sandman theory of the straight beam. But we thought it was important also to include these effects, to cover these effects in our course, because otherwise it would have been maybe not completely coherent accounting for finite curvature in the equilibrium equations, compatibility equations, without giving an explanation why we do not account for curvature also in the constitutive equation. So it's we can usually skip curvature terms in the constitutive equation because these terms become relevant, as you see, for ranges of curvature that are beyond the common values that are employed in civil engineering applications. Okay, I think that for today is enough. This complete machinery will be applied to some boundary value problems. We will analyze some arches with different shapes tomorrow with different distribution of loads, and we will see how all these sets, all those equations can produce distribution of axial forces, of shear forces, bending moments, and we will discuss these results in the final lecture of tomorrow afternoon. Tomorrow we are meeting at 3 p.m. So thank you for being with us, and we will meet you tomorrow. Thank you.
Grazie, arrivederci a domani.
Arrivederci.
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 Ciao.
Ciao.